In this video, we're going to start talking about free body diagrams. A free body diagram is a picture containing the body and all the external forces acting on the body. So one example, if we take this Boeing 77 in a steady level flight, where we know the acceleration is equal to 0, which gives us the sum of the forces will be 0. So first we have the weight of the aircraft. And as the aircraft is moving through air, it will generate aerodynamic lift. And similarly, along the velocity direction, this is a thrust from the engine, and there's a corresponding aerodynamic drag. So by sum of the forces equal to 0, we know the weight equal to the lift, and thrust force is equal to the drag force. So this is an example of a free body diagram. Notice that in a free body diagram, we don't have any other bodies except the ones that we're interested in, and all the other bodies will be replaced by their forces. The weight of the aircraft is the gravity force that the Earth exerts on the aircraft. But we do not include a picture of Earth because it has been replaced by the weight. A free body diagram should contain all available information on the forces, including magnitude, directions, and point of application. Okay. In order to draw free body diagrams, we have to understand forces. As we have talked about earlier, there are mainly two types of forces: contact force and non-contact force. And for non-contact force, we have shown the example of gravity attraction or gravitational attraction. And here we'll start looking at contact forces. And there are many types of contact forces, and let's start with the most simple one. So for contact force, we idealize a contact force by idealizing the body that exerts a force. So that is, if we take the simplest example, we idealize ropes, cables, etc. as a string. And a string is a one-dimensional body. And when it is taut or stretched, tightly and attached to another body, it exerts a force. And if the string is not taut, then the force exerted by the string is 0. And some definitions: the magnitude of the forces exerted by the string is called tension. And we also know a string always pulls and never pushes. So here I want to introduce two new concepts: straight string versus a curved string. By a straight string, if we have an object and the string is attached to the top of the object, and we have a taut string, and we can convert this diagram to a free body diagram as shown the forces or the tension exerted by the string and the direction of that force will be aligned with that string. Let me just put that in parallel. Now for a curved string, if the string is attached to a curved surface, let's use the color blue. This is the point of contact of the string on the curve. And we have a taut string. And if we were to convert this into a free body diagram, we know the forces will be tangential to the point of application. This is the tension T and direction. So mathematically, we can represent the force or tension due to a string as T bar. And T bar is equal to the magnitude times the direction. And T is the tension. And the unit vector u hat is either tangential to the string or into the string at the point of attachment. To better illustrate the concept of a string, let's look at an example. So we have a block of weight equal to 10-pound force, which is supported by 2 cables as shown. And we need to find the tension in each cable. So where do we start? So we start by defining the acceleration of the block. Since we're dealing with a static problem, we know the acceleration of this block is equal to 0 as well as velocity. But in this case, velocity doesn't really play a role because we are trying to find the forces. And if we use Newton's second law, we know the sum of the forces is equal to the mass times acceleration. And if we have a 0 acceleration, we know the sum of the forces is equal to 0. Now to model all the forces, we need to start drawing a free body diagram. So this is the block. And we need to replace Earth with gravity attraction. And we have 2 cables that's attached. And we know the direction is align the cable. So this is, let's call that T1. And T2 will be along the other cable. And we know the angles between the cable and the reference vector is 45 degrees and 30 degrees. So by sum of the forces equal to 0, so on this block, the sum of the forces is equal to the weight vector plus T1 vector plus T2 vector. Now we need to find individually what W bar, T1 bar, and T2 bars are. In order to define vectors, we need to define some direction. So in this case, we could use some E1, E2, and E3 as the reference frame. So we know W bar has a magnitude of W, but it's in the negative E2 direction. So this is equal to negative W E2. But what about T1 and T2? We know the magnitude of T1 is T1. But what about the direction? So in order to find the direction for T1, let's write T bar equal to T1 times U1. And U1 is the direction of the tangent T1. And from the geometry, we know that T1 makes an angle of 45 degrees with respect to E1 vector. So if I were to decompose this E1, E2, and some other unit vector, U1 hat, and it will make a 45-degree angle with respect to E1. Then we can find the component of U1 in terms of E1 and E2, which is cosine 45-degree E1 plus sine 45 degree E2. And similarly, we can find the direction for the second unit vector, which is the direction of the tangent T2. So U2 is equal to negative sine 30 degree E1 plus cosine 30 degree E2. Now using the same analogy here, we can write T2 is equal to the magnitude times the direction. Now we can write out the expression for T1 bar and T2 bar, which are T1 cosine 45 E1 plus T1 sine 45 E2. And T2 would have a magnitude of T1 times negative sine 30 E1 plus T2 times cosine 30 E2. This should be T2. Now we have an expression for T1 bar, T2 bar, and earlier we have found W bar. Then we can use the sum of the forces to find the component of T1 and T2. So we know the sum of the forces is equal to 0 and is equal to W bar plus T1 bar plus T2 bar. And let's replace all the variables that we have just worked out. We have negative W2 plus T1, and we know cosine 45 degrees, that's square root of 2 over 2 E1, and sine 45, that's square root of 2 over 2 E2. And for the expression of T2 bar, we have negative 1/2. That's a value for sine theta, sine 30 T2 E1 plus square root of 3 over 2 times T2 in the E2 direction. So let's recall, by a zero vector, when we say a vector is equal to 0, what we're really saying is that this vector would have 0 component in the E1 direction, and 0 component in the E2 direction, and 0 component in the E3 direction. So let's combine the terms with the same direction. So for E1, we have T1 square root of 2 minus then by zeroing out all the components, we have 0 equal to T1 square minus 1/2 T2. And we have 0 equal to the negative W plus T1 square root of 2 over 2 plus square root of 3 over 2 T2. Okay, now all we have to do is to solve T1 and T2. So of course you can find many ways to solve this. So the simplest way is we can use the first equation to find T2 is equal to square root of 2 times T1. And we can substitute t2 equal to square root of 2 times t1 into the second equation. Now we have 0 equal to negative w plus t1 square root of 2 over 2 plus square root of 3 over 2 times square root of 2 t1. And by solving this, we get w equal to t1 times the squared root of 2 over 2 plus the square root of 6 over 2. And we know t1 is equal to w over 2w over square root of 2 plus square root of 6. And then we know t2 is simply square root of 2 times 2w square root of 2 plus square root of 6.